This lecture is about nuclear fusion and fission and energy in nuclear equations. To start off, we can just define the two terms. Fusion is the joining of small particles together to give larger ones, and fission is the splitting of large nuclei into smaller ones. I have an example for each below. You can see in the fusion example, two smaller nuclei are combining into a single larger one. And in the fission example, a single large nucleus is being hit with a single neutron, which causes it to split into two smaller nuclei plus a few extra neutrons. You'll notice that in both examples, the nucleon and proton numbers are conserved across the decay. At the beginning and end of both equations, there are the same number of nucleons and the same number of protons. We remember from the last few lectures that to bond together, nucleons release energy. Binding energy is the energy individual nucleons have released in order to bond. This means that the more binding energy per nucleon an element has, the more energy each individual nucleon has released. So as we go up this graph, this tells us that more energy has been released by each individual nucleon. We can use a binding energy per nucleon versus nucleon number graph to understand something important about fusion and fission. Let's say that I have a particle of neon. I can see that that has 20 nucleons, so that's going to appear here on the graph, and the graph is telling me that neon has about 8 mega electron volts per nucleon. And let's say that I want to combine two neon atoms together into a single calcium atom. So this would be an example of nuclear fusion, where we're combining two elements together into a single larger element. Students looking at that fusion reaction might mistakenly assume that when these two elements bind together in fusion, they're just sharing their total binding energy and their total number of nucleons. And so no additional binding energy is added to this system. But that's not actually what's going to happen here, because I can see using this graph that the element with 40 nucleons is going to have more than 8 mega electron volts of energy per nucleon. So that means that when fusion occurs here, these two particles will not only bind together, but each individual nucleon will also release some additional binding energy. So if we start on the graph where the 20 nucleon number is and rise up to where the 40 nucleon number is on the energy value, I can see that as a result, each individual nucleon had to sacrifice some additional mass to gain some additional binding energy per nucleon. So what I'm trying to get across here is that when fusion or fission occur, the nucleons don't just share their binding energy with each other, because if they did that, the binding energy per nucleon wouldn't change. What also happens is that the mass of each individual nucleon drops to release some additional binding energy. So based on the definition of fusion and fission, fusion would involve the movement to the right on this graph because it involves going from a smaller nucleon number to a larger nucleon number. And fission would be going from right to left because that involves going from a larger to a smaller nucleon number. I know that iron, Fe56, is the most stable element. Before that, the binding energy per nucleon goes up, and after the binding energy per nucleon goes down. So I can see that on this side of the graph, if fusion occurs, if you move to the right on the graph, the binding energy per nucleon goes up. So that means that fusion releases energy, because binding energy is released energy from the mass of nucleons. So in the area to the left of iron, if fusion occurs, fusion is going to involve the release of binding energy. And looking to the right of iron, I can see that fission is going to release energy, because here, if I move to the left on the graph, which is what fission does, the binding energy per nucleon also goes up. So that means that each nucleon has to release some energy. What I'm trying to get across here is that to the left of iron on this graph, fusion is what's going to release binding energy. And to the right of iron on this graph, fission is what's going to release binding energy. Nucleons can naturally sacrifice mass to emit binding energy, but in order to gain mass, they need an external source of energy. This means that an atom can only change its nucleon number spontaneously when its binding energy per nucleon goes up. So what this tells us is that fusion and fission can only really happen spontaneously in atoms when they're gaining binding energy per nucleon. So that means that fusion occurs naturally to the left of iron and fission occurs naturally to the right of iron. But if we were to swap these positions, these reactions involve a drop in the binding energy per nucleon, so they require an external source of energy in order to occur. Those are the main facts about fusion and fission that you'll need to know. The last little piece of information is, where does released binding energy actually go when fusion and fission occur? When nuclear fission or fusion causes binding energy to be released, the energy is emitted as kinetic energy in the particles after the reaction. Particles always obey the conservation of momentum after they gain the kinetic energy from the reaction. So I'm going to talk about this more in a moment. I'm just going to do some example problems first involving fission, fusion, and binding energy. The first example problem we'll do is identifying fission and fusion. This is just asking you to identify the following reactions as either nuclear fission or fusion. I can see in the first example, two smaller particles are combining to make a single larger particle, and they emit a neutron as well. But the main thing to notice here is that a particle with more protons and nucleons exists after this reaction than did before. So this means that this is an example of smaller nuclei going to a larger nucleus. So that means that this is an example of fusion. Whereas in the bottom example, I can see I have a single very large nucleus of uranium breaking into two smaller atoms and three neutrons. So because this is a larger nucleus breaking up into smaller nuclei, this is an example of nuclear fission. So that's how you would identify which is which. We're now ready to talk about energy released in nuclear equations. Deuterium undergoes fusion according to this following reaction, and the following data are available for binding energies per nucleon in each individual particle. This is asking you to determine in mega electron volts the energy released by this reaction. So you'll remember that the energy released is going to be the change in binding energy before and after the nuclear fusion or fission event. In this case, this is fusion. So to understand the energy released, I just need to know the total binding energy before and after the reaction. So before, I know that the binding energy per nucleon of deuterium is 1.12 mega electron volts per nucleon, and I can see that there are two nucleons, so that means that the total binding energy in this atom is 2.24 mega electron volts. And it's the same here. I know that the binding energy here is 2.78 mega electron volts per nucleon, and there are three nucleons here, so that means that this is the total binding energy of hydrogen 3, and that last hydrogen atom only has one nucleon. And the function of binding energy is to bind nucleons together with other nucleons. And so if you only have one single nucleon, you don't need any energy to bind it to others because there are no other nucleons. So that means the binding energy of that last hydrogen atom is just 0. So I can see that the total binding energy before the reaction is 4.48 mega electron volts, and after it's 8.34 mega electron volts. So that means that these particles had to release additional binding energy in order to bind together. So just subtracting before from after, I can see that the total binding energy released is going to be 3.86 mega electron volts. So that's how much energy was released in this fusion reaction. Here's another example. A stationary nucleus of uranium-238 undergoes alpha decay to form thorium-234. The following data are available for the energy released in the decay, the binding energy per nucleon for helium, and the binding energy per nucleon for thorium. And this is asking us to calculate the binding energy per nucleon for uranium-238. So I know that alpha decay means the release of a single helium atom, which is why the equation is written in this way. So we just need to understand the total binding energy that exists after this alpha decay and use that along with the energy released to find the uranium's energy. Starting with thorium, I know that the binding energy per nucleon is 7.6, so I multiply that by 234 nucleons. And for helium, I know that it's 7.07 mega electron volts, and I multiply that by 4 nucleons. So these are the numbers that I get for the binding energy of each particle. So that means that the total energy after the decay is 1,806.6 mega electron volts. That means that the energy before the decay, because energy is being released from the mass of the nucleons, there's actually going to be less energy before the decay than after the decay. So I'm subtracting the energy released. So that means that before the decay, the total binding energy that exists is 1,802.31 mega electron volts. So that's the binding energy of the uranium-238 atom. So to calculate the binding energy per nucleon, I just divide that value by 238 nucleons, and I get a final answer of 7.57 mega electron volts per nucleons. So that would be the binding energy per nucleon of the uranium-238 atom. After decay, what is the value of the ratio of the kinetic energy of the alpha particle to the kinetic energy of the thorium nucleus? This relies on some concepts that we learned in previous units. If the uranium decays into thorium and helium, I know that the energy released is going to exist as kinetic energy in the particles. So that means that these particles are moving. And I know specifically that they're going to be moving away from each other because we assume the uranium is beginning with 0 velocity, and because of the conservation of momentum, the total momentum before and after the decay must equal 0. So this means the momentum of thorium must equal the momentum of the helium, because the two are canceling each other out. So we can use this to solve the problem. We can say that the kinetic energy of the helium over the kinetic energy of the thorium is what we're looking for. And there's a special equation for kinetic energy that relates it to momentum, where kinetic energy is equal to the momentum squared over 2 times the mass. And I know that here the momentum of each individual object has the same magnitude. because they're canceling each other out to 0. So that means that the momentum on the top and bottom are the same, and the 2's are also obviously the same number, so I can cancel those out. And when I cancel everything out, I'm left with this simple equation, where the ratio of the kinetic energy of helium to thorium will actually be equal to the ratio of the mass of thorium to helium. And because the difference in mass between protons and neutrons is so small, I can just count the number of nucleons for now and say the mass of thorium is 234 nucleons, the mass of helium is 4 nucleons, so that means that the ratio is 58.5. So that's how you would solve that problem. The next type of example is using a binding energy graph to estimate energy loss. This problem is asking us to use this graph to show that the energy released when 2 hydrogen-2 nuclei fuse to make a helium-4 nuclei is approximately 4 picojoules, which is 4 times 10 to the negative 12th joules. I can use this graph to understand the binding energy per nucleon of hydrogen-2 that's here. I can see that's about 1.2 mega electron volts. And the binding energy per nucleon of helium-4 is here. So that's going to be about 7.2 mega electron volts. So I know that I'm fusing 2 of these hydrogen-2 particles to make a single helium-4 particle. So I can just find the individual binding energies of each particle using the numbers that I got from the graph, and then compare the total energy before and after. So I can see that the energy change is 24 mega electron volts. So that's the energy released. So I just need to convert that to joules. First, I'm going to go from mega electron volts to electron volts. So there's 10 to the 6th electron volts for every mega electron volt. And then I can go from electron volts to joules. And when I do that, I see that this is roughly 4 times 10 to the negative 12th joules, which is equal to 4 picojoules. So that's how you would use this graph to find the energy released. The final question is just a comparison between mass and energy. In a fission reaction, the total mass and the total binding energy before the reaction are Mi and Ei respectively, where the binding energy is defined as a positive quantity. After this reaction, the total mass is Mf and the total binding energy is Ef. Which of the following correctly compares the total masses and the total binding energies? In a fission reaction, the total mass and the total binding energy before the reaction are Mi and Ei respectively, where the binding energy is defined as a positive quantity. After the reaction, the total mass is Mf and the total binding energy is Ef. Which of the following correctly compares the total masses and the total binding energies? So I know that for both types of reactions, binding energy is released. So there's going to be more binding energy after the reaction than before. So I already know that Ef will be greater than Ei. So now we just need to figure out what's going to happen with the mass. So this graph shows the nucleon number going down, but that's actually not really a correct way of reading it, because I'm trying to understand what's going to happen to the total mass, and nucleons are conserved. So each individual particle after the fission is going to have less nucleons, but this is asking about the total mass. And in total, there will be the same amount of nucleons present as before. They'll just be split up into multiple particles instead of existing in one single particle. So that alone doesn't tell me whether the mass is getting bigger or smaller. However, I do know that each individual nucleon had to sacrifice some mass to get that additional binding energy, because I know 100% that there is more binding energy than before. So that means that each individual nucleon must have sacrificed some mass. So because there are the same number of nucleons as before, just split up into more particles, and each individual nucleon sacrificed some mass, I know 100% that there must be less mass than before. So M final is going to be less than M initial, so the answer here is going to be D. And that's everything that you need to know about fusion, fission, and energy in nuclear equations.